The number 2 strategy that I'll list here is actually dropping rows from the data. In other words, ignoring the observations that have missing values on the variable or variables that you care about. The huge problem with this method is that it can lead to bias. In other words, lead to systematically getting the wrong answer if your pattern of missingness is either missing at random or missing not at random, either of those, okay? Because we've seen that the values that are missing, right, whether a value is missing is correlated with what that value is if you have missing at random or missing not at random. And so just ignoring those values is going to lead us toward the wrong answer. This does work. This method is okay if the pattern of missingness is missing completely at random. And that's because, again, remember that missing completely at random is just like randomly removing part of your data. It's just like having a smaller sample size. So it won't systematically affect your results in any way to have data that is missing completely at random. Now, it's important to note here that we don't actually know what kind of missingness we have in any particular situation. For any real data set, you don't know whether it's missing at random, missing not at random, or missing completely at random. Based on what we know about the data collection and based on what we can see in the data set, we're going to have to guess and hope, but we do not know which type of missing data we have. So although the effectiveness of the strategies that we're listing depends on which kind of missing data we have, again, for a real data set, we do not know which kind we have. We have to use the best information available to us to try to figure it out. Again, that involves knowledge of the data collection method and thinking about it. It also involves looking in the data to see, for example, if the values that, the rows that are missing on a certain variable tend to have particular values on some other variable. Another thing to say about this strategy of dropping rows from the data set is that it's the default in most statistical software. Now, I don't think this is actually a good thing because I think it's important for you to know when you have missing values and for you to try to do something about it. So let's think about a couple examples. There's a statistical software package that's common in some fields called SPSS. I do not like SPSS very much for a variety of reasons. The main one is that people who use it usually don't end up using reproducible code. It is possible to use reproducible code in SPSS, but the way SPSS is set up, it doesn't encourage you to do that. And so for that reason, SPSS is not that easy to use. But one thing it does, which is great, is that every time you analyze a data set, it has this little preamble at the top. It posts some information, which includes the number of values that have been removed from the data set before the analysis was completed due to missingness. And I think that's great because it's constantly reminding you, hey, some of the data is removed when we do this analysis. You may have started to notice how R deals with missing data. Some functions like mean just will not give you a result if there are NAs. So if you take the mean of a vector that includes NAs, you will not get a result. You'll get an NA. And I think that's a good thing. I think that you should have to explicitly deal with your NAs in some way. You should know that they're there and deal with them. On the other hand, if you do, say, a linear regression in R or almost any other software, suppose you have 10 different predictor variables and each of them is missing for different rows. What most software will do is remove any row that has at least one missing value on it. If there are a lot of columns, that could lead to removing a lot of rows, right? If each person in the data set is missing on one of the 10 columns, you'll lose everybody. There won't be anybody left in your data set if you try to run a regression that includes all 10 of those columns. So that's not ideal. And also, when you run a regression in R, it does not have any kind of alert or warning that missing values have been dropped. You have to notice by looking at the degrees of freedom, in the very bottom of the output, we'll see where as we go forward. But you have to kind of check whether the degrees of freedom are as you expected or whether the sample size seems to be smaller than you wanted it to be, or even better, deal with the missingness before you even run the regression.